Our next unit is on probability. And although you and I probably don't necessarily set probability things, we're exposed to that a lot. Whether it is that we buy a lottery ticket or we go to a casino and gamble, maybe take a little trip to Las Vegas or whatever, probability plays a big part in what we win or what we don't win. And I want to share one story with you. It was a few years ago that the National Math Teachers had their conference in Las Vegas. And normally this conference was over the weekend, like maybe a Thursday, Friday, Saturday. And this particular year, it was a Tuesday, Wednesday, Thursday. And I remember being disappointed because I ended up not going. I would have had to miss too much school. So a couple months later, I was talking with one of the people that had helped organize it, and I asked him, why was this the case that we went in the middle of the week? And his response was, it's because the people in Vegas did not want 10,000 math teachers in their hotels over the weekend. Mathematicians tend to be a little bit conservative about their gambling. They really know what it means to gamble, so either they're really conservative or possibly they're really good card counters. So one of the two, they just didn't want them there. So what we're going to look at with this this next unit is just kind of generally how probability is determined, and we're going to look at probability, and we're going to look at odds, and we're also going to look at a concept called expected value, so that you can actually be a smart gambler. I'm not encouraging gambling necessarily, but it's good to know really what you're getting into and what the reality is about what you're doing there. I mean, there are other things in life that are determined with probabilities. You know, the probability that it's going to rain tomorrow, or the probability that you know, something is going to happen. We are exposed to that regularly. So we're going to just look at how that is determined and how we can do calculations and be smart about making choices that involve probability. So let's talk about probability. And a couple of the things that we need to do is just make some definitions of terms, but also it's important for you to not make probability overly difficult, because it really can be boiled down to a couple real basic principles. When we're talking about probability, we're asking, you know, how many ways can this happen? What if I see, and it kind of goes back to patterns, if I see something happening, what's the probability it's going to happen again? What are the chances that it's going to happen again? And so mathematicians kind of put together some concepts that will help us to look at that. One of the really key pieces of any probability is considering the sample space. The sample space of any experiment is the total number of outcomes. And in particular, it's a listing of those outcomes. So if you look on the page that talks about probability, we'll see some example of sample spaces there. If we have a die and we're going to roll that, we can get a 1, a 2, a 3, a 4, a 5, or a 6. So I've listed all of those there. If I am going to toss a coin, I'm going to get heads or tails. If I toss 2 coins, they could both be heads. The first could be heads, the second tails. The first could be tails, the second heads, or they could both be tails. So when I'm looking at my sample space, sometimes it's really helpful to actually write that all out so that we can see how many possible outcomes we have. So the probability ratio is relatively simple. All we're looking at is favorable outcomes, I'll define that here in a minute, to total number of outcomes when we're looking at this. There's you'll see this oftentimes, you'll see this notation in math texts or statistics books. that'll look something like this. They're just saying like probability of the favorable outcomes, probability of total. Sometimes we'll see this, the probability of some event happening, all right? We're going to boil it down to this. And what we mean by favorable outcome is what we're asking for. So if I'm rolling a single die and I ask, what's the probability I would get a 3 when I do that? My favorable outcome is a 3. So the question I'm going to ask myself is, on that die, how many 3s are there? So there's only one 3. That's my favorable outcome. I have one favorable outcome. The total number is 6 because I've got 6 numbers on a regular die. Similar, if I'm tossing a coin and I want to know the probability of getting heads, I have one head on that and I have a total of 2 possible outcomes. So keep that in mind. Our probability ratio is simply looking at favorable to total outcomes. And that's a really important piece to remember. Always boil it down to that. Even if you've got a problem that has more than one probability involved, take each of them and boil it down to this ratio right here. Okay, so what I just described to you is what we'd call single stage. So I'm rolling the dice or tossing the coin. Occasionally we will also have an example where we're talking about a multi-staged experiment. Okay, so here's an example. This is what we would look at for this one. When we're looking at multi-stage, it's like we'll do one thing and then we'll do another thing. And we're looking at how those two combined together would be our probability, our total probability. Within multi-stage experiments, we have 2 types that we look at. We look at independent events and dependent events. These words in this context are the exact same thing you and I think of independent and dependent being when we're not talking about math, okay? So let me do this, I'll do an example here. Here's an experiment. What if I say, an experiment is conducted to determine the probability of drawing 2 face cards from an ordinary deck of cards. So I want to know the probability of 2 face cards when I choose 2 cards, okay? If I have an independent experiment, what it means is that whatever I do the second time hasn't been at all impacted by what I did the first time. If it's dependent, something has been impacted. And so a lot of times they will talk about this one as with replacement. And this one without replacement. You'll see how that plays out in this particular example, okay? So I've got a deck of ordinary cards. So there's a total of 52 cards. If I consider a face card a king, a queen, or a jack, then I know in each of my suits I have 3 face cards. So if I'm looking at a total, the total number of face cards in any one deck, I'm going to have 12 face cards. So if I want to get 2 face cards, then I know my favorable outcome is a face card. So for this first piece, I have 12 out of 52. So let's say I've got these cards in front of me and I reach in and I grab that face card. I had 12 out of 52 chances that was going to happen. Now, because I want this to be independent, that face card that I just drew, I'm putting it back. I'm putting it back in the deck. And now when I go to draw that second one, because in order for it to be favorable, I had to have gotten one on the first time, I'm going to still have 12 out of 52. Now remember when we talked about the counting principle and we said that we could multiply one event times the next event to give us the total number of possibilities. We do that exact same thing with probability. So if I have a multi-stage experiment, and I have two parts to it, and I did have two parts because I needed to get two face cards, and I was picking them one at a time. What I'm going to do is I'm going to multiply those two probabilities together. So my total probability is going to be the multiplication of these two probability ratios. Okay? If this were a dependent event, so I'm got those cards out in front of me, I reach in, I pull out a face card. Kind of boring right now, but the probability I would get a face card is still 12 out of 52. I'm going to take that face card and I'm putting it in my back pocket. So now, what I'm going to do the second time really was influenced by what I did the first time. How many face cards do I have left in front of there if I put this one back here? Well, I only have 11. And how many total cards do I have? I have 51. So my probability if these two events were dependent is 12 out of 52 times 11 out of 51. So think of this, I replaced the card the first time, and that was an independent event. I did not replace it the second time, and that was a dependent event. Okay, so we've talked about the probability ratio as being favorable to total. Now we're going to talk about a concept called odds, which I think probably we hear maybe even more often than we do probability. I have to tell you, I don't know why odds are needed, because they really give us the same information that probability does, but it's just a different way of looking at the information. So when we talked about probability as being favorable to total, what we're looking at with odds is more of a ratio of this to this, not out of total. But if I talk about odds in favor of something happening, the ratio that we use will be favorable outcomes to unfavorable outcomes. All right, so favorable outcomes to unfavorable outcomes. If I talk about odds against, I'm just flipping that. So I'm saying unfavorable to total. Oh no, unfavorable to favorable. So let's look at an example. So an example I have here, it says, the weather forecaster said the probability it will rain tomorrow is 7 out of 10. So the probability here is 7 out of 10. What we know is that probability is favorable to total. So in this example, my favorable number of outcomes is 7. There are 7 ways it will rain. I've really considered a total number of ways to be 10. So if I want to determine how many unfavorable outcomes we have, what I have to do is I have to take the 10 and subtract the 7. So that unfavorable is 10 minus 7, or 3. So think of it as there's 7 ways it will happen, there's 3 ways it will not happen, and there's a total of 10 ways. So now if I want to look at my odds in favor, I would say that we now are talking about a 7 to 3 ratio. Or sometimes you'll see this written like this. All right, because it's not, I mean, the whole thing tells us the total, but it's really a ratio of favorable to unfavorable. So it's kind of part to part. If I want to know the odds against, it's going to be 3 ways it won't happen and 7 ways it will. Or we could write this as 3 to 7. So when we're dealing with odds and we're dealing with probability. Basically, if we know any one of those ratios, we know all three. If I said to you that the odds in favor of you loving this class right now, at this moment, were 10 to 1, all right? What I know is if I were to take a poll here, that in this particular case, favorable, loving this class, would be 10. Unfavorable would be 1. I also would know that the total possible ways would be 11. So if I was given odds in favor as 10 to 1, I was given favorable to unfavorable. I could determine odds against. My odds against are going to flip this. So my odds against in this particular case would be 1 to 10. My probability in this particular case would be 10 out of 11. So if I know any one of these three ratios, I know all three of them. And my suggestion to you would be, if you're given one and you're asked to determine the other two, be really specific about, notice how I wrote out what I knew just from the ratio I was given. I think sometimes we forget to do that, and then we don't put the right numbers in. Determine favorable, unfavorable, and total. And once you have these three, you have all of those ratios. So one of the things we determine expected value for is to determine whether or not something is a fair contest. Mathematically speaking, fair just means break even. So whatever I pay out, I should expect to get back. If any of us think that that's true in any kind of a gambling setting, you're a little crazy, because it's not ever going to be true that either we come out ahead or that it comes out even. It's why they call it gambling. Okay, so in this particular one, it said we would get $8 if two heads occur. If you look at the sample space earlier in this packet, you will see that there's 1 out of 4 chance that we'd get two heads. Okay, and we're going to multiply that by $8 if that happens. The next one said that we would get $4 if two heads, if one head occurs. Okay, so we have $4 if one head occurs, and remember that's going to be 2 out of 4. So I just simplified that to 1/2, and that's going to be times $4. And then we don't get anything if it happens to be two tails. So we can write this out, but it's not really going to help us a whole lot. So that again would be 1/4, and this time times 0. So when I calculate this, I have $2, I have $2, I have nothing. So the expected value of this particular contest would be $4. Now remember, it said earlier in the problem that I paid $5 every time I played that game. So if I'm comparing $5 to $4, I would say this is not a fair game. My expected value is not the same amount as what I paid for that game. One of the things that's really important about this is just to know that, again, that's never going to happen. It's not going to happen very often that they're a fair game. The one example I want to share with you is, I don't know how many of you ever watched Deal or No Deal, but that was a really fun game show where you had all of the suitcases up there, all the briefcases, and you had to pick. And remember, after each time someone picked, that the banker put up a new amount that they'd pay for people to walk away. The reality is what the banker was doing was, between each of those picks, well, I'm sure a computer was doing it, but they were figuring out the expected value of what was left. So they were able to determine, in fact, what they could offer and still, in terms of probability, kind of stay within their means of what they were going to pay out. So expected value is good for us to know in terms of what we can actually expect to get for any kind of a contest that we're going to play.